Arpit Shah, and I'll be taking you through this demonstration of estimating daily evotranspiration. And let me begin first by telling you where I shortlisted my area of interest. I chose Punjab as it is a state well known for its agricultural output, in particular for wheat and rice respectively. Within it, I chose a region between Jalandhar and Ludhiana, two urban clusters, and in the zoomed in view, you'll realize that this particular area is dominated by agricultural fields, farmlands that is. Evotranspiration studies are typically done and impact agricultural zones, and this was one of the important factors why I chose this particular region. Now, as part of the workflow, it is not only important to identify the AOI, but then it is also important to download the precise geographic extent of the AOI itself, which is why I chose this website, geojson.io, to download this particular data. It also allows me to have a different view than Google Map, because the timeline for this particular capture is also different. So you can see that in the harvest season, the agricultural fields are much more lusher, greener, that is. Let me adjust the map view slightly so that the area of interest is completely visible in the view. Thereafter, I'll use a rectangular polygon based selection tool to highlight my area of interest. I prefer using this particular website for downloading the coordinates of my selection, because it allows me to download it in a particular file format which is accepted at several points within the subsequent workflow, which is the WKT or the well-known text format. Once I have downloaded the file, I'll move it from the downloads folder to the dedicated folder for performing this study. It is very important to have the material and information in a particular folder organized in a systematic way. It makes the processing much more easier. We can open the WKT file in a notepad or any other text editing tool. It contains a couple of lines of code which we will use subsequently. Another important aspect which I would like to highlight is that there is a significant landmark, the Satellite River, which passes through our area of interest. Some of you may know that evotranspiration studies are very useful for performing the irrigation management. So it also acts as a landmark, as well as subsequently, if there is any meaningful result, it can also help in irrigation planning as well. Now we will use the Copernicus Open Access Hub, which is a website from where you can download the satellite imagery, Sentinel-2 and Sentinel-3, which is required for performing this study. Using the polygon tool from the right, I am drawing a small rectangle and going to the search section, wherein in the filters I'll put the timeline of sensing period, essentially the capture of satellite imagery, as between 15th and 31st of May 2022, which is essentially a peak summer period. Thereafter, I will proceed to the Mission Sentinel-2 section and click the checkbox. I'll select the MSI-2A product, which is essentially the atmospherically corrected product. We needn't put the cloud cover percentage, although you can input a very low percentage at the very beginning, because we need a product which is cloud free. The search results show that there are 3 MSI-2A products in this particular time period. So what we'll do is explore the topmost product, which looks cloud free, as in there is limited white pixels which denote clouds. This is essentially an optical photograph. The cloud cover percentage is 0.16, which is very, very low. Relative orbit number is something which I typically note. The geographic extent of this image is also shown. So our area of interest lies to the bottom half towards the east side, and it is relatively cloud free from the as inferred from the photograph as well. Then we proceed to download this imagery. If it is an old product, then the imagery is not directly available, so we need to wait for some time, and when the product has been downloaded by the open access hub, it becomes available, and then we can proceed to download it. So I'm just showing to you from the card section certain products which I have previously downloaded. So once they are available, the offline mark disappears and we can straight away proceed to download it. For this exercise, because I had performed this tutorial myself before, I had already downloaded the requisite imagery, and what I will do is move that imagery from my earlier folder to the new folder which we will use for performing this particular study. The nomenclature is Sentinel 2A followed by the instrument, followed by the date, and followed by the time of capture. It is important to note that the rectangular polygon needn't be exactly matching the area of interest. So you can make a very small rectangle which forms a part of area of interest. You need to match that the polygon is the output of the satellite imagery is basically covering the area of interest. That is the only thing you would need to note. Now that we have downloaded the 2A Sentinel 2 product, we also need to download the Sentinel 3 product. So again, we'll do the same. We'll select that our particular area. We didn't use the satellite platform because that's not necessary. For the sensing period, for doing this tutorial, plus minus 10 days from the Sentinel 2 imagery is suitable. So I'll select that particular period. Because 27th of May was the period of the Sentinel 2A imagery, I'm inputting 17th of May to 7th of June as my preferred timeline for downloading the Sentinel 3 imagery. Thereafter, in the product type, I have to note that I will select the LST sensor, which is the land surface temperature sensor. Again, the instrument is basically the LST instrument over here. And the product level is L2, which is a higher level of processing which has been done. Now, in this particular time frame, there are 57 products which are available. So I will look to reduce the clutter by narrowing down the selection. How will I do that? I will visually scroll through the imagery output and see some of the images which are appealing to me and which timeline they are captured. So the images with the red spots indicates to me that there is a wider deviation of temperature values in those images. So I am essentially looking for imagery which has a higher temperature because it being a summer month. So I am narrowing down my timeline from the initial 20 days to the first 4 days of June. And so now we have just 10 products appearing as the output. All these 10 products cover our area of interest, but then I still want to narrow it down further. So if from the imagery output, the first image appears appealing to me. So what I will do is I'll select that output and then see the relative orbit start number, which is 333. So this is the path which the satellite takes at regular intervals. So I will basically in the filter section add that relative orbit start number as well, so that the images which are in the same geographic extent gets filtered out. So in this particular time frame of 4 days, there is just one product. So in this product, our area of interest lies right at the southeast section of the image. This particular product is offline as well, and I had already added it to the cart before because I had performed this tutorial initially by myself. So in the image view, as I have told you, we can compare and see where our particular imagery lies. So it lies bang in the dark red section, which I don't know whether it's the right method, but I found it that okay, out of the particular imagery output, this particular image looks appealing because of the higher relative temperatures on this particular date. What I will do again is to move the Sentinel-3 output from earlier folder to the new folder in the base section. Now we have both the Sentinel-2A as well as the Sentinel-3B images. So I am not extracting the Sentinel-2 imagery from the zip file because the software can directly read it from the zip file itself. However, Sentinel-3 images needs to be extracted from the zip file because the software cannot read the product directly from the zip file. What is the software? It is Snap, and I'm using the version 9. I can recommend you to install the All Toolboxes package of this software as per your operating system, were you to choose to do this Evotranspiration tutorial by yourself. There are a few important resources also which you should be familiar with, such as esa-sen4et.org, which will give you access to the all-important Evotranspiration plugin, as well as a user manual which would guide you in its installation as well as performing the workflow itself. GitHub.com contains a dedicated page on Evotranspiration wherein you will get the updated plugins script files. These script files are updated as and when a new issue in the workflow is found out or a new version of Snap is released. There is a dedicated Evotranspiration community forum as well on the Snap forum page. This particular forum has enormous content on the various types of issues other users have been facing, and if you were to have a unique issue, you can even create an account on this particular forum and post your queries. The resolution is typically very quick. There is a particular version of Python 3.6, which you would need to install first before installing the Snap software, and link the executable file in the Snap software configuration phase. So Python needs to be configured with Snap, and only a particular version, which is 3.6, is compatible with the Snap software for doing the Evotranspiration study. The downloaded script files which you have downloaded from GitHub needs to replace the default script files. So within the user directory typically lies a SEN-ET snap scripts folder. The script files which you download will need to replace the default script files here. Not only the scripts, but then there is also two other folders, the graph folder as well as the LUT folder, which will need to be replaced. Next, I'll take you through a few aspects in Snap which you should be familiar with before even you perform the tutorial. The software, once installed, needs to be updated on a regular basis. If you are a new user operating the Snap software for the first time, as you continue watching the video, I think you'll be familiarized with how the software appears, how it works, and how to process satellite imagery on it. Initially, we will use the File Explorer to locate the Sentinel-2 zip file. Once we click on it, the product is loaded in the Product Explorer view. Within it, I can go to the bands section and visualize the imagery by clicking on any of the bands. The imagery is visualized right now. Our area of interest lies close to the Satellite River on the southeastern section of the image. The user manual which we had downloaded earlier is also a very good reference point. You can use it to understand the literature on evotranspiration, the method of computation of Daily Evotranspiration using the SNAP software. Alongside, you will get diagrammatic representation of the processing workflow as well as very detailed processing steps. However, that document is not an updated one. So there is a technical review document which you can access from the community forum, the website of which I had showed you earlier. This particular document has certain corrections, it expands on certain points, and it will allow you to perform the tutorial on SNAP in a much more seamless manner. What I have done is I have captured screenshots of the processing flowchart from the earlier user manual. This particular flowchart is for the Sentinel-2 processing steps. The ovals represent the input data, whereas the rectangles represent the processing steps. So there are 4 distinct processing flowcharts. The Sentinel-2 I had shown you earlier. This is the processing flowchart of Sentinel-3. Again, when I will do the exercise, I will take you through these in detail. There is ERA 5 meteorological data, the processing flowchart of which you are seeing. And the last processing flowchart is the computation of land surface energy flux. So these are the 4 flowcharts. I have kept them as screenshots so that whenever I want to refer them in the tutorial, both for my understanding as well as to demonstrate it to you, I can use it accordingly. It is very, very important to basically organize your folder where you will be locating both your input and output data. You can have distinct folders for each of the workflows, although for the sake of this tutorial, I am doing it in one folder itself, all the processing flows. The plugin file which we had downloaded earlier, I have already installed it, but then you can go to the plugin section from the tool view and install that particular plugin by opening it and clicking on the 13 files within it, which contains the scripts to the tools which are used in the Evotranspiration study. So you'll have to click on the add plugin button to do that. Once you have installed it, within the optical and thematic land processing section, there is a SEN-ET folder which contains the 13 processing steps. One tweak which I have made is to amend the cache memory reserved for the software. By default, it's a low figure, but then I have increased it to a value 80% of my total RAM capacity, which is 16 GB. So one has to input the cache size in MB. And because the Evotranspiration is computing intensive, having a high cache memory helps in performing the processing workflow in a quicker manner. Now that we are familiar with the resources at our disposal and having set up the SNAP software as well, we can now proceed to perform the first workflow, which is to process the Sentinel-2 imagery. We have already downloaded it before, so the next step is to run the pre-processing graph. We will click on tools and go to the graph builder tool within, and fortunately we do not have to build the graph ourselves. It comes pre-built as part of the Evotranspiration plugin which we had downloaded and installed earlier. In the C drive, typically there will be the Sentinel scripts folder within which you can find the XML file containing the pre-processing graph. 4 outputs are generated as part of this step: the biophysical output, the reflectance output, the sun zenith output, and the bandmass mask output. In the read section, we will see that the correct product is being used, which is the Sentinel-2 image. In the resample section, we are essentially telling the software to standardize the resolution of all the bands within the Sentinel-2 imagery to a standard of 20 meters. In the subset section, again, the parameters are preloaded. So these are the bands which are useful for Evotranspiration. The remaining will be deleted from the revised product. So you would realize that subsetting is necessary because typically the Sentinel-2 image is very large in size. So not only is it intensive on the hard drive, it also is intensive in terms of the computation which are done subsequently on SNAP software. So to perform the computation in a smaller area is much more preferable and quicker to do. And this is where our WKT file, which contains the coordinates of our area of interest, will be useful. So we've copied the coordinates and pasted and clicked on update. So the yellow polygon is the area of interest and it lies completely within the larger red polygon, which is the Sentinel-2 imagery. The biophysical output will have 5 layers, which is the leaf area index layer, photosynthesis layers, and a few other layers, the technical details of which I will not be explaining over here, and it can be found in the user manual itself. We need to ensure that the output is being written to the correct folder so that we can recall it whenever we like if we were to switch off the software. Again, the remaining parameters are pre-built, so we do not need to adjust it. All we need to ensure is to paste the correct directory to write the output in. And we do not need to go and select that folder every time. We can just copy the path of our output file location and just paste it over here. Once all the parameters are set, wherever manual intervention needs to be done, we will be in a position to run the particular graph. At a macro level, you will need to be familiar with what evotranspiration is to make better sense of the processing steps. So because evotranspiration entails the transfer of water from the soil surface and vegetation, processing the optical imagery where the source of energy is sunlight is important, because we will be able to know where exactly the sun position is, what is the location of and the extent of vegetation in our area of interest, how much photosynthesis is happening at that point in time, and so on and so forth. So now we'll click the run button and Snap will solve for the output and save it in our processing folder, which we had selected earlier. The time taken for this operation is significantly reduced because we had clipped the original Sentinel-2 imagery to our area of interest. Once the operation is done, there will be a success message, as well as the 4 resulting output layers will be saved and published in the Product Explorer section. Not only are they published in the Product Explorer view, they are also located and written in the processing folder, which we can double check right now. Yes, it has been written over there exactly as we wanted. We will open a particular band of the reflectance output, and straight away we can see that the area of interest is being visualized over here, the landmark being the Satellite River on the south. We open the Sentinel-2 original imagery product and lay the area of interest view side by side. Both are the same reflectance bands, and we can see that the area of interest clip which has been done is accurate because it was located on the southeastern section of the original image. And moreover, the Satluj River acts as a good visual cue as well. Next, let me show you a few ways to basically interpret the particular imagery output as well. So it's not just a visual feature which you see on your screen. There are mathematical figures, components which are part of the output. So using the color manipulation tab, you can see the min, max, average, the histogram of the figures which are generated as part of the output, which contains essentially the reflectance details. Thereafter, let's open the sun zenith angle product. From the visuals, we aren't able to discern much, but seeing the pixel values, we see that there is a 17-degree sun zenith angle. Sun zenith angle is the difference between the angle of the sun's rays and the direct vertical. Because the imagery was captured at dawn at around 5:30 am, so the angle is very low. Let's open the cloud mask now. It is completely white in color with a pixel value of 1 across all the pixels, which is not surprising because if you remember, the Sentinel-2 imagery data set had a very limited cloud cover, and particularly our area of interest had a non-existent cloud cover. Next, we open our fourth and final output of the pre-processing graph, which is the biophysical product. F cover is the fraction of vegetation cover, LAI is the leaf area index, and LAI underscore CW is the canopy water content. I'll not enter into a technical explanation of these concepts, but in the eventual computation of daily evotranspiration, these particular layers are very, very important. And you will notice that in the subsequent workflows, we'll use this particular biophysical product layer quite often. As a next step, we will move to our computation of elevation. We've completed the pre-processing and we'll now use the cloud mask layer to generate a elevation graph as well as a land cover graph. Now, why do we use the cloud mask layer? No particular reason as such, because it is a relatively lightweight layer and it covers our area of interest predominantly. So it's not because it is a cloud mask layer, but because it is a layer which covers our area of interest, which is lightweight. We go to the graph builder again and load the pre-built elevation graph. We'll select the SRTM 1sec HGT auto-generated elevation layer, which Snap will automatically download. We just have to ensure that the folder which the product is written to is the correct folder where we are saving our rest of the material. This processing step doesn't take much longer to complete, and we now have our elevation layer. The bright yellow spots are the ones with the highest elevation after the white color, that is, and the blue and the green spots are the one with the less elevation. So we can adjust the color combination to suit our visual interests. Our next step is to compute the land cover. Under normal circumstances, we would have used the land cover graph, which comes as part of the Snap Evotranspiration plugins scripts, and generated this particular layer by using the cloud cover layer as our input layer. But upon doing so, I found that the output was coming as blank, as in with a null value, and several other users also had the same issues, which is why an alternate way which to do this particular step is to download the land cover layer from the Climate Data Store from climate.copernicus.eu. You can download a zip file based on the year of your interest. So I downloaded a land cover layer. The latest which was available was for the year 2020. So from the zip file, we'll have to extract the .nc file because Snap cannot read the land cover layer directly from the zip file. So we'll have to extract that file and load it separately onto the Snap software. Once we do so, we'll have to do a different step, which is to co-locate the area of interest from this particular land cover layer, which is actually for the entire world. So we do not need such a large layer. So we'll use the subset function, but from a different command, which is the co-locate layer. So what we are essentially asking the software to do is from our area of interest, which is depicted by any of the previous layers from pre-processing which we had generated. I'll use the cloud mask layer as an input, and for the slave product, I will denote it via the downloaded land cover layer. So what I am asking the software to do is to locate the area of interest from the master product and generate a new layer from the slave product, which only covers our geographic extent of the area of interest. So the co-location step doesn't take long to complete, and the output, which is the land cover layer, will be visualized shortly using the LCCS_class_S layer. Yeah, one thing which you can again observe is the Satellite layer onto the south of the land cover visualization. So the land cover, basically, if you see on the bottom left of your screen, you have different types of layers as classified by the Climate Data Store, be it a agricultural land or a vegetated land or a forest or a river, etc. So the land cover map again is vital in the computation of evotranspiration. Just if you are curious to know how did the original land cover map look like, the visualization will be on your screen in just a moment in time. As you are seeing, the visualization is for the entire globe. So we do not need the complete land cover layer for the globe, which is why to subset it to our area of interest, we use the co-locate tool. One thing to note over here is this is not the final step in the computation of the land cover layer, because the name of the layer LCCS_class is something which we need to change, because in the subsequent processing workflows this name will not be accepted. So we'll have to change it to a particular predetermined name. So we'll use the subset command to do so. The subset tool which we just used helped us to remove the non-important layers and keep just the land cover layer, because this is the layer which will be used in our subsequent workflows. We've not renamed the layer just yet. Even before we do that, we will just standardize the nomenclature which we have used across all our layers, and in that interest we will change the name of the product to a more relevant one, which is the CCI_land cover. So this is not a technically necessary step to do so, but aesthetically it is important for us to keep the layer names as product names as standardized. To change the layer name, which is still unchanged, we'll have to right click and go to the properties and change it from there. So CCCI land cover -2015 is what the evotranspiration script in the plugin will accept, which is why this step is crucial, without which in the subsequent steps the Snap software will throw up an error. So renaming the layer and saving the product subsequently using the CCI land cover name is crucial. The next step is for us to generate the leaf spectra, also known as the leaf reflectance and transmittance layer. So we'll have to go to the optical tab, the thematic land processing tab, SEN-ET, and select this particular operator. As you would have noticed, this is not a graph based operation. There is a dedicated tool in the plugin which is there for us to use. The source product which we will use to generate this layer is the biophysical layer which we had generated earlier. The target product, we will rename it as output_LRNT, which is in short for leaf reflectance and transmittance. We will also ensure that this product is saved in our directory where we've been saving all the other outputs, which is the processing layer. So this is an important step, and thereafter, because this page, which is the input/output parameters tab, is complete, we'll move to the processing parameters and select first the display execution output. The black box is generated below. Subsequently, we will click on the output images section and put it to our processing folder once again. Over here, it is important for you to note that we'll have to save the image as per the name of our layer and add .dim, which is the file format of the image over here, before clicking the run command. So this step we'll have to do it on repeat mode in most of our subsequent steps. So it is important to notice. Because we had selected display execution output, we can also see from the black box that what are the steps being taken, whether there are any errors, any warnings, etc. are also reflected. So I use the display execution command also. The product has now been generated, and we can see that the leaf reflectance visualization on the screen. Again, the technicalities of which is something which we will not discuss. Those who are savvy about it can basically see the readings and understand what is the reflectance properties of that particular green vegetation in that area from the layers which are generated in this particular product. The subsequent step involves the estimation of the fraction of green vegetation. If you would remember, while computing the biophysical product, one layer which was generated was estimation of the fraction of vegetation. Now this is a more advanced step, which is the estimation of fraction of vegetation which is green. So again, we'll go to the same location and select the fraction of vegetation operator. The sun zenith angle and the biophysical product are used to generate this layer. So two source products are there. Again, the same principle applies. We'll save the target product as per our preference, which is FGV, a short for fraction of vegetation which is green, and save it in our processing folder as our directory. So if we do not want to go step by step and select the same layer processing folder, we can also copy the layers' path name and paste it over here. So both options are there. The parameters, the minimum fraction of vegetation is green is 0.2. We will not change it. We know that the minimum fraction of green vegetation in our area of interest is much higher than 0.2 or 20%. That is. Again, we'll ensure that the name of the output image is the same as the name of the layer, and also include a .bim extension towards the end of the output image for the product operation to run successfully. Again, the tool does not take very long to run. We'll just note that the products are getting saved in the processing folder, and subsequently we will now open the FGV product from our Product Explorer tab. So the white pixels are the pixels where the fraction of vegetation is green. So as I had indicated to you earlier, our area of interest has majority of the pixels as green because in the peak summer period, the fields, agricultural fields are ready for harvesting, and therefore the fraction of green vegetation is high, as you would see from the geojson.io visualization on your screen right now. Hope you are enjoying the video demonstration on computing daily evotranspiration thus far. Feel free to read the article on evotranspiration on Mapmyops' geoblog, the link of which is mentioned in the video description. Feel free to share our content with your near and dear ones and in your personal or professional network as well. Having derived the leaf reflectance and transmittance layer as well as the fraction of green vegetation, we are now in a position to go on to the next step, which is the computation of structural parameters of the vegetation. This step, the operations remain the same. We go to the operator in the SEN-ET folder, which is the snap plugin on evotranspiration. There are three source products which we'll have to select: the Landcover, the biophysical product, and the fraction of green vegetation, all of which are open in the Product Explorer window, which is why we can select it. Otherwise, we'll have to click on the three dots and locate the layer from the directory. Thereafter, we would have to rename the target product and save it. So we've renamed it as VSP, which is in the short of vegetation structural parameters, and are saving it in the processing folder. So once this step is done, we are in a position to go on and fill in the processing parameters from the next tab. The Landcover band over here, as you would see, is CCI Landcover -2015, which is one of the reason why we had to rename the Landcover band earlier, because the script is structured in that way. There is a number of output, right from vegetation height to fractional cover to canopy height to width ratio, all of these being structural parameters which will be generated as an output of this particular operator. we'll again save the image in the processing folder and with the same name with the extension .dim. Before we hit the run button, there is another component which we have to add in. This time it is the lookup table. The lookup table of the Landcover is already supplied to us as part of the Snap plugin. This is a lookup table for the CCI Landcover. Lookup table essentially contains the parameters, dimensions of the Landcover, and because we are using CCI Landcover, it is necessary that the lookup table is matching or compatible with the CCI Landcover. So if you are using a Landcover from a different source, then you have to create or supply with a new lookup table which is compatible with that. Now that we are ready with this inputs and our parameters, we are in a position to run the tool. As the number of inputs and the parameters increase, as well as the number of output increase, the time taken for computation also typically increases. In some locations in the video, I have fast forwarded it so that it is in the best interest of the viewers. The vegetation structural parameters product is written and all the bands are also there. We are currently opening the vegetation height band and you can see the dimensions, and which would be better visible in a more colored format. The darkest red are the locations where the vegetation canopy is the highest, whereas the white color portion, which is the Satluj River, is where the canopy height is non-existent, which is why it is in the white shade. So this layer is the vegetation fractional cover. So again, the areas where vegetation is there, which is essentially the agricultural farmlands, they are colored initially in red, and I have changed it to reflect it in the white color as well. So we can play around with the colors as in how the viewer wishes to visualize it for presentation subsequently. We can even open all the layers, output layers, and stack them side by side if you want to study them or visualize them. Our next step is to estimate the surface aerodynamic roughness. This is the last step in the Sentinel-2 processing chain. Aerodynamic roughness allows the transmission of water vapor from the soil and the vegetation into the atmosphere. So the smoother the surface, the quicker the water vapor transfer in a very simplistic terms. So because we had estimated the vegetation structural parameters such as canopy height, reflectance, photosynthesis values, as well as the biophysical product earlier, these two inputs go into this operator of estimating aerodynamic roughness, and we will rename the target product and save it in the processing folder. The same name goes into the processing parameters tab, and .dim extension is also included so as to allow the operator to work without facing any issues or errors. The soil roughness assumption is 0.01 meters, which is pre-built into the script, so we will not change it because as it is a very low figure. We will now run the tool, and in a short time the output will be ready in the Product Explorer section of the software. There are two bands which form part of the aero roughness output. One is the roughness length and the other one is the zero plane displacement. Again, these are technical outputs. If you wish to know more, you can Google them and you will be in a better position to understand the concepts technically. We've completed processing Sentinel-2 optical imagery, and we are now ready to move to the next step, which is processing Sentinel-3 imagery, which is not optical but thermal in nature. Let's see the processing diagram. It begins with downloading the Sentinel-3 data, pre-processing it, wrapping it to the Sentinel-2 scenes projection, and then sharpening the land surface temperature band, which is the last step involved and our ultimate objective of processing Sentinel-3 imagery. Because we've already downloaded the data, it is time to load that particular data set onto the Snap Explorer view. And as I had indicated to you earlier, we cannot load it straight away from the zip file downloaded from Copernicus Hub. We have to extract the contents from the zip file and go to the xfdu manifest.xml file. The XML file is readable in Snap, and we are able to easily open the particular product in the Snap's Product Explorer view now. As I had indicated, the LST band, or the land surface temperature band, is the most important band over here, and logically you can relate to it as well, because evotranspiration involves the thermal transfer of water vapor from the soil and the vegetation into the atmosphere, which is the reason why it is crucial for us to have a very micro level depiction of land surface temperature for our evotranspiration studies. Please note, the Sentinel-3 pre-processing graph will not load in the graph builder straight away. There will be an error message which will be shown. This is a technical defect, and to address it, we will need to make a few manual adjustments. First, you will need to open the Sentinel-3 pre-processing graph in a notepad, and the path where your Sentinel-3 dataset is saved in your system, you will need to paste it in the first section of the Graph.sys code. Subsequently, what you will need to do is to insert the area of interest sys geographic coordinates. If you remember, in the Sentinel-2 pre-processing, we had downloaded the WKT file from geojson.io, which represented the geographic extent of our area of interest. You will need to copy that couple of lines of code and insert in the graph file in a few areas, as I am highlighting in the screen right now. The third and final major type of edit which you will need to do is to insert the path where you wish the output of the pre-processing graph to be saved in your system. So in our case, we are saving all our output in the processing folder. So I'll just copy the path to the processing folder and paste it in a few sections of the Sentinel-3 pre-processing Graph.sys code. Once we have made these three major categories of edits, we will save that particular graph and it will get updated, and we will be able to load it in the Snap once again without any issues. I had already edited and saved that particular graph before, so I will just go to that particular folder and load the updated graph from there. Now the graph has successfully loaded, and you will see that there are a few processing steps which we will need to do, beginning first by subsetting the product, reprojecting the product, and generating the three output, which is land surface temperature, observation geometry, and cloud mask. An important thing to note over here is we need to insert the reprojection details, so without which the graph will not successfully execute its operation. Where will we be able to find the reprojection details? From the Sentinel-2 imagery, we will be able to find that because we had reprojected the dataset even there. So we will go to the Reflectance product, and within the metadata section, we will open the granules, the level 2A tile product, and open the geometric info section, within which, double clicking on tile underscore geocoding, we will find the dataset under the value section. What we will do is we will need to be in possession of this information. So let me open a notepad and save the reprojection details. The last line, which is horizontal underscore CS underscore code, has a particular reprojection details, which is EPSG 32643, which I am saving, and this particular data will be important for us when we execute the Sentinel-3's pre-processing graph. So let's go back to our workflow once again and load that particular graph and make that edit and run the pre-processing graph. Before we do that, just to show you, the subset function will only keep the LST related band and the cloud underscore IN band. The other bands which come as part of the Sentinel-3 product are not needed. which is why we are subsetting it. And because we had already inserted the geographic extent in our code, we would not need to do that once again in the Snap software itself. In the reprojection area, as I had indicated, we will need to open the predefined CRS and select the particular code. We would not need to copy and paste it. That particular code we'll just need to find from the list and highlight it in the particular reprojection section, that is. Subsequently, the next steps are not something which we will amend the parameters. Those are predetermined and pre-built into the graph. So again, it is subsetting the observation geometry, the land surface temperature, and the cloud mass to our area of interest. So that is the steps which are there as part of the pre-processing graph, and we will just ensure that the product is written to the correct folder and named as per our preference. Because we've added the reprojection information to our graph has been updated, and it would be a good practice to save the graph as a new copy rather than running it straight away, which is why we will go to our graphs folder and save an updated copy. Now we are finally in a position to run the pre-processing graph of Sentinel-3 imagery. The output has been successfully written and the products are now visible to be explored in the Product Explorer section. Let's first examine the observation geometry product. There are 4 bands, latitude, longitude, and a couple of zenith bands. Next, let's examine the cloud mask product. There are a few black pixels in the cloud mask, which denotes clouds. Some of you may wonder that the Sentinel-2 cloud mask was completely white, as in devoid of clouds. Then how is Sentinel-3 having clouds? That is because both the images were captured at 2 different days. Next, let's open the land surface temperature band. This is a thermal band, it's not an optical imagery, and you will notice that it is blurry. It is because the Sentinel-3 resolution is 1000 meters compared to Sentinel-2 resolution, which is 10 meters and above. Yet, despite this being a thermal band, you will be able to spot the Satellite River to the south of the image because the temperature of the river is much less in comparison to the surrounding areas. 316 degree to 327 degrees Kelvin is the range of the land surface temperature over our area of interest, which is equivalent to 43 to 53 degrees centigrade. You may wonder, this is a very unbelievable number. This is because it is not an actual temperature. Land surface temperature is the temperature on the surface of the ground, as in how the temperature would feel if you touch the surface. And often the surface warms up significantly more due to prolonged exposure to sunlight. The next step in the Sentinel-3 processing flow is to run the warp-to template operator. This operator essentially asks Snap software to run an algorithm on the observation geometry of Sentinel-3 product so as to make it of a higher resolution. And therefore, the template image which we will use is the Reflectance product of Sentinel-2. As I had already indicated, Sentinel-2 has a higher resolution, and because the observation geometry of Sentinel-2 satellite is different to that of Sentinel-3 satellite, the algorithm helps standardize and upgrade the Sentinel-3's observation geometry by using the warp-to template operator. The fundamentals remain the same. We will save the product at our processing folder, as well as the output image will have the same name with a .dim extension. We can choose any algorithm from the processing parameters, but I have chosen to keep the default. Why do we feel the need to enhance the land surface temperature, which is our ultimate objective in the Sentinel-3 processing flow? It is because evotranspiration studies are done at a farm level, and Sentinel-3 product is not suitable for doing so because it has a resolution of 1000 meters. In comparison, the average farm size in Punjab is 3 acres, which is why not only in Punjab but across the world, a combination of Sentinel-2 and Sentinel-3 output will enhance the observation geometry and subsequently the land surface temperature to a resolution which would enable to do farm level studies on evotranspiration. Let's examine the output of the WOP2 template. Straight away you will be able to see that the output of the product observation geometry, that is much more smoother. Initially, if you would recollect, the output was much pixelated, as you are able to see on your screen. Now, because it is of a higher resolution, the output is much more smoother in nature. As a next step, finally, what we will do is to sharpen the land surface temperature band. The bedrock of this particular step is the enhanced observation geometry, which we had already generated in the previous step. So now let's go to the Sentinel-3 plugin and run the particular operator. The reflectance product, land surface temperature product, elevation layer from Sentinel-2 image, as well as the new observation geometry, which is the higher resolution one, along with the cloud mask of Sentinel-3 are forming the inputs of the sharpened land surface temperature operator. Again, we will choose to rename the output as convenient and save it in our processing folder. We will also keep in mind that we save the output in the processing parameters to the same name and with the .dim extension. Besides that, a few important additional parameters which we would need to insert is the exact date and time of the capture of the Sentinel-3 imagery. It is called overpass. So the first few digits alphanumeric in nature from the Sentinel-3's output would give us the date and time of the Sentinel-3's overpass, which we will insert over there. The other processing parameters, we will choose to keep it as default because these are accurate and technically sound. For example, the name of elevation band as generated as part of the Sentinel-2 processing flow is also called elevation. It is important for you to know that I have presented a error-free approach as demonstrated in the video workflow thus far and even subsequently. In reality, when you will be doing the workflow yourself, you may encounter a whole lot of errors. I had encountered several errors which took me days to resolve, and some errors I was only able to observe the impact after I had done a few subsequent steps, which is why doing the basics right, which is to have the correct input-output parameters and having the same output image name, adding a .dim extension, all these would relatively make your task of determining the daily evotranspiration much more smoother. Besides that, I've tried to cover as many technical points, revisions, etc. in the video workflow. So if you were to choose to do the workflow yourself, you will certainly not commit as many errors as I had done during my first and subsequent attempts before making this video. The product has been successfully written after executing the Sharpen LST operator. Let's examine the sharpened LST band. Straight away, you will observe that the resolution of this band is much more clearer. The original LST band as visualized right now was of a much lower resolution. Now we are able to see the image along with the cloud pixels in a very accurate manner, which indicates to us that the output has been written in an accurate way. We have now concluded the Sentinel-3 pre-processing flow and are now ready to commence the ERA5 pre-processing workflow. Having determined the vegetation structural parameters from Sentinel-2, the land surface temperature from Sentinel-3. Now it is time to download the meteorological data, which is the ECMWF ERA5 Meteorological Reanalysis Dataset, which comprises of several variables such as wind speed and air temperature, which helps us to ascertain what is the rate of water vapor transfer from the surface to the atmosphere. While I have personally set up my system already, new users would firstly need to register a new account on Copernicus Climate Data Store. Subsequently, you will be given access to a URL and a unique passkey, which you will insert in a .cdsa.pirc file, which would act as a bridge between your system and the repository where the meteorological data set is stored online. The actual installation of CDSA API client needn't be done. That already comes part of the Evotranspiration Python package, which Snap automatically downloads as and when you operate a processing command via it. However, if you face an issue, you can visit confluence.ecmwf.int and do a step-by-step installation of the API itself. Please note that you will need to save the file with the .cdsa.pirc extension in the user directory of your C drive. On the website guide, it is mentioned that you can create this particular file format by using Notepad. However, I don't think that is the right method. On your screen is a screenshot which would give you a simpler technique. You'll just have to go in command prompt and type in a phrase of code, which would automatically create this particular file with the correct file format for you. Subsequently, you can move that file in the user directory of your C drive, and then you are good to go and your system would be set up for you to proceed and download the ECMWF ERA5 Meteorological Dataset. Let me begin by showing you the video demonstration or how to go about doing so. We return to the Snap software. We click on Optical Thematic Land Processing SEN-ET plugin, and the operator is download ECMWF ERA5 Reanalysis data. We can name the target product as we like. I have named it as the ECMWF ERA5 dataset and added a _ Punjab, which is where my area of interest lies. Subsequently, we will also need to add the directory where we want to save the output, which is the processing folder. In the processing parameters section, Snap will first ask you to input the geographic extent of the area of interest in a particular format, NWSE, which is northwest southeast. An easy way of finding this particular information is to click on any of our previously generated output layers and go into the navigation pane. You will see the product layer will be captured in a red outline, which essentially is the geographic extent. Next, you will hover your cursor on two parts of the globe. One is on the northwest edge of the product and the other is on the southeast edge of the product. On the bottom of your screen, you will find the latitude and longitude details. So, for the northeast section, you can denote the latitude and longitude, which will form NW part of the equation, and on the southeast section, you can note the latitude and longitude, which will form the southeast portion of the equation. So, as you would have noticed, we needn't have the area of interest's geographic extent matching precisely to the product. It can basically be a large area also, just that it needs to cover the area of interest. So, I have already captured this particular information for my area of interest previously. So, I will just open the notepad where I have saved that particular data. You must also note that this particular data needn't be in decimals. Snap only will accept whole numbers. So if the coordinate is 32.5, you can actually insert only 32. Just ensure that the area of interest is covered. So our area of interest lies comfortably within 32 and 75 degrees northwest and 30 degrees and 77 degrees southeast. The start and end date of downloading the meteorological data will be one day prior to Sentinel-3 imagery capture date and one day post the date of capture of Sentinel-3 imagery. Because our S3 imagery was captured on 4th of June, the start and end date will be 3rd and 5th of June 2022 respectively. All the other parameters are to be kept just the way they are because we need all these data sets. And the file to which download data is to be located in the processing folder once again. But this time, one thing to note is that we will not save the file name with the .dim extension as we had done in the previous steps. This time you will save a netcdf file where the output will be written, and netcdf is represented by a .nc extension. So you will need to save the file as a .nc file. This will automatically download and write the product in the netcdf format from the API client interface of Climate Data Store. We can now run the operator and download the meteorological data. It will hardly take a minute or two for Snap to download it. There won't be any error messages subject that you have set up the API interface correctly. The .netcdf file format, which contains our meteorological data, is also successfully written in the processing folder. We can even choose to visualize the meteorological data. However, as you would see, it is not optical imagery and there is not much to be gained by visual analysis of the imagery output. However, enthusiasts can go to the color manipulation tab and see the pixel values and infer the attributes which they would like to discern from the imagery output. Our next step will entail the mapping of the meteorological data which we have just downloaded at a surface level of our area of interest. To do so, we will utilize the elevation layer which we had generated as part of the Sentinel-2 processing workflow previously, as well as the timeline of the capture of the Sentinel-3 imagery. So once we have selected the operator from the Snap Evotranspiration plugin, we will insert the source product as the elevation layer. And our target product, we can rename it as per our preference. Also, we will ensure that we save this particular output in the processing folder as we have done in all our previous steps. In the processing parameters section, firstly, we will need to reference the file where we had downloaded our meteorological data to. It is the same file with the .nc or netcdf file extension. Besides that, we will also need to enter the date and time of our Sentinel-3's imagery capture. Ours was captured on 4th of June 2022 at 5:26 am in the morning. Besides that, Snap also asks us to enter the time zone of our area of interest. This can be easily figured with a Google search just in case we do not know. Punjab lies in India, which is GMT plus 5.5 hours. However, you will find that Snap will only accept an integer value, which is why the area of interest is closest to GMT plus 5 and we enter 5 as our figure. Besides that, all the other values remain constant. We need Snap to derive all the bands of comprising wind speed, vapor pressure, air temperature, etc. The final thing which we will do is save the output image with the same name and with the .bin extension as we had done numerous occasions before. We are now ready to run the tool. The product has been written successfully and now we can visualize it from the layer which is visible in the Product Explorer section. The air temperature values are mentioned, just as the other layers are also captured. Not much can be gleaned by visually observing it. Now that we have prepared our meteorological data, we are ready to move on to our final processing chain in our workflow, which is the energy flux and daily evotranspiration computation. Let's observe the processing workflow. Land surface energy flux modeling will begin with us estimating the Longwave irradiance. Thereafter, we will estimate the net shortwave radiation. These output we will combine with previously generated output from the Sentinel 2, 3 and meteorological data computation to determine the all-important land surface energy fluxes layer. Finally, we will be able to compute the daily evotranspiration using the energy fluxes layer. Essentially, what we are doing over here is to see how much energy is being discharged from the surface into the atmosphere, which will help us to calculate the evotranspiration. The meteorological data which we had prepared forms the source product in this particular operator. We can rename the Longwave irradiance output layer as per our preference and save it in the processing folder. In the processing parameters, we will leave the inputs as they are as default. The air temperature measurement height is 100 meters, which is also accurate. We will save the product with the same name in the output image section, just with the extension of .dim. We are now in a position to run the estimate atmospheric Longwave irradiance operator, and the output has been generated and the layer is visible in our product explorer section. We can visualize the layer and see the irradiance values which are generated. Subsequently, we will now generate the net shortwave radiation. We'll select the operator once again. Over here, there are multiple inputs. Firstly, we will need to input the leaf reflectance and transmittance product generated in our Sentinel 2 processing. Similarly, we will select the biophysical product, vegetation structural parameters product. The meteorological input product will be the prepare meteorological data step which we had, output of that step which we had done in our last processing chain. The solar zenith angle will be from the Sentinel 3 processing chain where we had warped the observation geometry. We will rename the target product as desired and save it in the processing folder. In the processing parameters, the visible soil reflectance and near infrared and soil reflectance values are to be kept as default. So what we need to do is to just save the output with the same name with a .dim extension. The output has been generated. Let's visualize the layer. There is a shortwave radiation for the canopy as well as a shortwave radiation for the soil. And both the outputs are drastically differing from each other because the radiation emitted from the soil is much more higher than the radiation emitted from the canopy of the vegetation. We can also visualize the bands side by side by stacking them using the feature available on Snap software. Our next step is to compute the all-important land surface energy fluxes. Land surface energy fluxes uses one source energy balance model for bare soil pixels and two source energy balance model for vegetated pixels to derive latent, sensible and ground heat along with net radiation. In the parameters, we will include the Sharpened LST layer along with the warped observation geometry. Both of them were the output of the Sentinel-3 processing chain. The leaf area index is nothing but the biophysical product. Alongside vegetation structural parameters, fraction of green vegetation, aerodynamic product needs to be inputted. All of the above which I had just mentioned are from the Sentinel-2 processing flow. Besides that, we will also need to include the meteorological output of which we had prepared, as well as the previous two outputs which we had generated, which are the shortwave and the longwave, radiation and irradiance respectively. Sentinel-2 mask, which we had generated as part of the pre-processing chain, also needs to be included as one of the inputs. Subsequently, we are in a position to go to the processing parameters, just that we need to ensure that the name of the layer and the directory are the one as we desire. The parameters, we will keep it just the way they are, and we will click the soil emissivity layer outputs bands which we definitely want to generate as part of this processing step. We will enter the output image with the same name and with the .dim extension. We are now ready to run the processing tool, and the output has been generated. As you will see, there are numerous bands which are generated as part of this detailed layer. This is because the energy fluxes is a complex phenomenon which basically says to us how much energy is being discharged from the soil as well as the canopy into the atmosphere, which is a prerequisite step in terms of determining the evotranspiration. So I have opened a few layers: sensible heat, latent heat, long wave radiation, and those who are enthusiasts can examine these particular layers and study the pixel values and see the energy fluxes. This layer by itself is very important. However, we will use a portion of it to estimate the daily evotranspiration. What daily evotranspiration does is extrapolates instantaneous latent heat flux using the daily solar irradiance. We will select the operator from the same location. We don't need to insert many source products, just the energy fluxes product as well as the meteorological data which we had prepared as part of our previous processing chain. Once again, we will name the product as desired and save it in our processing folder. In the processing parameters, there is no parameters for us to input, so we will just go to the processing folder once again and save it with the same name with a .dim extension. We are finally in a position to run this operator and derive our estimation of daily evotranspiration. When I had practiced this workflow myself prior, I was literally very much overjoyed at reaching this particular step. It was a very painstaking process. We can visualize the daily evotranspiration layer in a better way by color coding it in a few colors. The yellow and red sections of the image are the ones with the highest evotranspiration, the unit of measurement being millimeters per day of water vapor, that is. The daily evotranspiration over our area of interest ranges from a minimum of 1.3 millimeters per day to a maximum of 6.1 millimeters per day with an average of 3.8 millimeters per day. Daily evotranspiration is not captured over water bodies as well as over cloud pixels. I hope you enjoyed this journey, and I hope to see you again soon. Bye.